This video is about energy, springs and materials, and I'm going to assume that you have already watched the video B7 about springs. If you haven't, then please go back and watch that now. When a force extends a spring, energy is stored, and the elastic potential energy of the spring is increased. The equation for elastic potential energy for a spring is written here. That is half multiplied by the spring constant multiplied by the square of the extension. There are two ways of deriving this equation. One of them is graphical, the other uses integration. If you're interested in the integration way, I'll show that at the end. But let's quickly draw a graph of force versus extension for this spring. Because force and extension are directly proportional if Hooke's law is obeyed and the spring is not extended beyond the elastic limit, then we will get a straight line passing through the origin of a force versus extension graph. The mass that's been placed on the bottom of this spring has been displaced through a displacement equal to that extension. The work that is being done by that mass is equal to the force multiplied by the displacement. However, here you can see that the force is a function of displacement because the displacement is the extension. So what we're saying here is that the area between the line and the x-axis is the work that is done. If we were to increase an extension of a body from x1 to x2, then the work done in increasing that extension would be equal to the area shown shaded in yellow on this graph. You can determine that area by using the trapezium rule if it's a nice straight line like this, or by breaking the area into different shapes and finding the area of each shape. Or if it's a curve on your force versus extension graph, you would count squares. Depending on your exam board, you'll either be told that half of a square or smaller counts as no squares, and half of a square or bigger counts as one square, or you may be told that any part square, regardless of how big it is, counts as a half square. There are different ways of doing it. When you count the squares, you then multiply the number of squares by the work done represented by the area of a single square. It's important to remember that when we talk about the area of a single square, we mean look at a single square, look at the change in extension, and look at the change in force, and multiply those two together to find what the work done is. Often in questions where you are asked to find the work done in stretching a spring, you will have to calculate the spring constant as part of that question. As the area of a triangle is half multiplied by the base multiplied by the height of the triangle, the equation for elastic potential energy can be determined by working out the area of the triangle. And so half multiplied by the base, which would be the extension, multiplied by the height, which would be the force. But as force equals spring constant times extension, we can substitute that in, and that gives us this expression here. To derive the expression for the work done in extending a spring, and therefore the elastic potential energy, using calculus, we follow these steps. The work done is the force multiplied by the displacement. But as the force is a function of displacement, then we have to integrate across small intervals in displacement. The function of displacement is the spring constant multiplied by that displacement. And when we solve this integral, we get half ks squared. But because we have limits to our integral from 0 to x, the extension, the expression falls out as half kx squared. This isn't required for your A level.